Hello AP Chemistry and welcome to 19.4 Entropy Changes in Reactions, where we put some quantitative aspects of entropy to work, right? So first, there's this diagram in your book, and I just want to make sure that we're crystal clear here, right? So here we have increasing temperature, right? And what happens to entropy over the course of some state changes, right? So obviously, as we increase the temperature, right, we go from here, where our entropy would be 0, right? And it's only ever 0 when we are at, right, when temperature equals 0, right? And then we increase, and then we hit melting, right? And we'll see that this is a directly north line, right? There is not a change in temperature, right? But instead there is a huge increase in entropy. What does this remind you of? Right. It reminds you of, hypothetically, right, heating curves, right, that we talked about last year, where these plateaus represent our state change, where there's no change in temperature because, right, the energy is going into the breaking of bonds or making if we're going, or coming out of the making of bonds if we're going the other direction, right? And likewise, we see the same thing here, right, where there's no change in temperature at that point in time, right, but we get a huge increase in our entropy, right, and we get a bigger one. Here, right? Because as we boil it, right, that's when we get rid of, we have so much kinetic energy, there are no more attractions between the molecules, right, or the atoms, and they are free to move independently, right? Which is why the increase in entropy is greater there than it is for melting, right? Likewise, when we looked at heating curves, right, the plateau was longer because there we have to break all the intermolecular forces, right, as opposed to just weakening the IMFs, right? So anyway, entropy things we should know. All right, same equation that we used previously, right? The sum of the standard entropies of our products minus the sum of standard entropies of our reactants. Thing to take note of here, right? So standard molar entropy units, right, have a temperature component in them, right? As in it is joules per mole Kelvin, because temperature is directly linked to entropy, and we'll talk a little bit more about that soon, right? And you'll note, right, again, none of these have entropies of 0 because, right, the only things that have entropies of 0 would be if we were at 0 degrees Kelvin. Okay, so then if we wanted to use the standard molar entropies to calculate the standard entropy change for the following reaction, right, we would go find our product. So we would go find aluminum, we would go find water. This would be times 2, this would be times 3, right? And then we would subtract off the sum of our reactants. Yes, does that make sense? I don't think we need to work that out. And that's it. Hello AP Chemistry and welcome to 19.5, where we introduce the concept of free energy, right? And one of the statement from your book, right? In any spontaneous process carried out at constant T and P, the free energy always decreases, right? Which means that if we have a negative delta G, right, as in free energy decreasing means being released from the system, right? It's a spontaneous process and those things go together, right? Better than spontaneous, we would say thermodynamically favorable, right? Meaning that our thermodynamic state functions, right, G, H, and S, say that this process should occur without outside intervention, right? Going back to what your book emphasized in chapter 5 and at the beginning of chapter 19, right? That just because something is thermodynamically favorable, meaning these state functions of G, H, and S say it should happen, right, says nothing about the time frame for which it should happen, right? That's kinetics, which we'll talk about in chapter 14. That would tell us how quickly whatever it is should happen, right? And equilibrium, right, which is kind of what this stuff is talking about, right? Equilibrium tells us to what extent it actually happens, right? So note that all this is saying, and all we are saying in chapters 5 and 19, right, is the likelihood of something happening. Like, should it happen on its own? Yes or no, right? And why, right? But it doesn't tell us the rate at which it will happen. We'll learn that in chapter 14. Nor does it tell us the extent to which it'll happen, right? As in the concept that we've been operating under for the last year or so of chemistry, right, is that if we know the amount of reactants, obviously we can calculate the amount of product, right? But the assumption there is that all of it would convert to product, right? But a lot of chemical reactions don't actually work that way and have a natural stopping point known as equilibrium. And stopping point's not quite right, but a place where it comes to rest, right? And so if we look here at this diagram, that's what this diagram is trying to show you, right? Is that if we have a whole bunch of just reactant, then it will spontaneously proceed towards here, right? Where that is the negative free energy for this process, right? If we have a whole bunch of reactant, right, it will spontaneously head this way also, right? To that point, right? And the Q and Ks, we'll work that out later when we get to that unit, chapter 15, I believe. But the point is every reaction has that point, right? And so it will be spontaneous as long as it's heading in that direction, yes? All right, so let's talk about how we can calculate the free energy of a process, right? So note that the delta G of a process, right, is equal to these things, right? Why do I keep doing that? Minus, I did that in 5 too. Products minus reactants, same thing as before, right? And so doing this shouldn't be a problem. Note that this is like our delta H again, right? Where when we said our heats of formation, right, that's the amount of thermal energy exchanged to make that substance from 1 mole, to make 1 mole of that substance from its constituent elements, right? Same thing for delta G, which means that the same things that would have a 0 heat of formation have a 0 free energy of formation, right? And you could use your appendix to come up with those, and it would be the same exact thing. Yes, the same calculation we've done before. So I'm going to assume you know how to do that. If not, see me. For the combustion of propane, for the other one, it's a little bit more thoughtful. So it says for the combustion of propane at 298, do you expect delta G to be more or less negative than delta H, right? Which requires us to think about that equation, right? If we know that delta G equals delta H minus T delta S, right? And then we know that combustion, what kind of delta H does combustion have? Right, it has a negative value, okay. And then if we look at our reaction, can we predict the sign of delta S? Absolutely, right? We've got 1 and then 5, so we've got 6 moles of gas over here, and we've got 3, 4, 7 moles of gas over there, right? Which means, right, increase in entropy, which means a positive delta S, right? Which means that, and T is always positive because it's in Kelvin, which means that this is a positive term. So if I subtract a positive term from that negative, then delta G is, right, more negative, right? Does that make sense? Okay. Fantastic. This is our introduction to free energy. Stay tuned, and in the next one we will discuss this equation at length and that little table from your guys' book to make sure you can qualitatively discuss all the aspects of this equation. All right. Thank you for listening. Be good, and I will see you soon. Bye.